Hello. Quite often I try to take time to repair some of my kids' toys, and I figured I'd start a little channel on how to do some minor electronic repairs around your home. Oftentimes I do them to save myself some money. What I have is a little Hot Wheels electronic toy, and before it was completely tore up by my kids. You could press a button and it would make lights and sounds. There are bits and pieces missing, including the rubber that was on the wheels itself. And I want to say at one point, because of how rough my kids are with the toy, that the motor stopped working. I don't know if it's because maybe some gears were stripped out, or maybe something was broken internally with the electronics. But I'd like to at least dissect the current condition, as in it's not working at all. And even if I flip the switch, it was in the off position. I can press the buttons even when that switch is in the other position. It still doesn't make noise or work. Now, simple things. To give you a background, I work on electronics in the aviation realm, not specifically on aircraft, but on instrument landing systems on an airport. Systems such as an localizer and a glide slope, tactical air navigation system, VOR or VHF Omni range, air to ground radios or air to ground or ground to air to ground radios, some switching systems and stuff. I say that just to let you know that I've got a little bit of electronics background, but by all means am I not an expert. Simply put, because most of your electronic repairs around the home are based on electronic principles, and a lot of what I do has a basis in it. If you don't put it into practice often, you tend to forget it. So a lot of things I do around my house when I repair them, and the reason why I'm starting a series of videos, is simply just to keep me familiarized with different electronic things, and it does benefit me on at work, as well as it benefits us at home, because instead of replacing this toy with another new toy with very young kids that it would just get torn up again, I can at least get this functioning to an extent, I believe, by lights and sounds. Now, I'm not looking at fully repairing this car. I have zero expectations of replacing gears or replacing the DC motor in it, as I do not have readily available spares. But I do want to fault diagnose this car a little bit, and at least try to get it to make sounds and make lights and indications of some type of function again. So the premise of this video is to try to teach maybe some low-tech and some high-tech ways of troubleshooting around your home to do small type of repairs. What I have with me is a tool set by iFixit that I'll use for dismantling this. I've also gotten some other things that I've procured over the years. I've got this little Craftsman multimeter. I believe I acquired it from Sears many years ago. It's not the best, it's not a fluke, but it serves its purpose as a hobbyist. The one item that I have that enables me to do a little bit more things, or a couple more things at home, is I also keep try to shift my camera a little bit. I also keep an oscilloscope at ready, as well as a hot air reflowing station and soldering iron, primarily because at points in time I was reballing and repairing PlayStation 3s when people were throwing them away during the yellow light of death, and had a little bit of success. Sometimes, as everything's a learning experience, a lot of failures before I was able to repair those items. And some of them I resold and some of them I kept, just because for me it's more of a hobbyist kind of thing than it is a job. But that being said, I'd like to move along and get into this repair a little bit. Now the first thing I'm going to do is gain access to the batteries. And knowing my kids, as they're pretty rough with their toys, I would suspect that, and I can already see it here, there's been a little bit of water or some kind of damage in here. And you can see a lot of corrosion around the batteries themselves and the terminals. I suspect that the batteries are dead, or at least close to dead. Each battery should measure about 1.5 volts DC. Now the simple thing that you could do at home is just get new batteries and swap them in and see if they'll work. And I'll do that here in a second. But I do want to show you alternate ways of checking batteries to see if they're good. One can be with a multimeter. If I set it to volts DC, and I set it to a low range of that scale, 20 volts DC, I can make a measurement with my negative lead and my positive lead across these batteries. Now, something just out of practice that I often do on the job is ensure my leads are good, whereby I set them into the low scale of being able to take an ohms or continuity measurement, and I touch my leads together, and there should be little to no resistance across the leads. As you see, it's bouncing around a little bit because these leads are fairly old, but again, I'm a hobbyist. If I make good continuity, I'm getting 0.2 ohms of resistance, occasionally bouncing up to 3 and 4. Now, you don't ever want to leave your multimeter in this type of measurement when you're going across a live voltage, because what you have is the internal battery voltage coming across these leads in order to take a measurement to provide you how much resistance is across these wires. If you were to do that in something with a little more voltage and come across batteries or a power supply source, you could potentially create an arc because you have the difference in potential between your voltages, one from your leads and another from the battery, whereby you could either damage your multimeter itself. You also could potentially electrocute yourself. But I'm setting my multimeter back to the 20 volts DC range. And these batteries, I can tell you, are wired in series just by looking at the plates and how they're configured. You have a negative terminal going to a positive terminal that's going to be linked up to the next negative terminal, or excuse me, linked up to this negative terminal, going to this positive terminal, and so forth, so on. Whereby you go negative to positive, negative, or negative to positive, and then back negative to positive. If these were in parallel, all your negative sides of these batteries would be wired together, and so would the output of the positive side. Now if I take my leads, and I'll try to do this without getting in the way of the video, and I put my negative lead to the negative side of the first battery, and a positive lead to the positive side of the last battery. As each one of these batteries, and they're wired in series, should be around 1.5 volts. Then 1.5 times 3 would give me about 4.5 volts. I can see by my multimeter that I'm only measuring about 1.12 volts across all three batteries. I can equally check each individual battery, and I can see that this battery is no good because I'm only seeing half a volt. Although I will also say, if you want to get a more accurate measurement, the battery itself needs to be not wired in series. And if I was to pop the battery out and take a measurement from the positive terminal to the negative terminal, you can see that that voltage is going to vary just a little bit. But that battery is no good and will need to be replaced. This battery as well, I suspect to be no good and will need to be replaced. As a matter of fact, this is probably the only halfway decent battery, because as I remove it from the circuit and measure it independently, we can see how much charge is remaining on this battery. Well, you got 1.45 volts. I suppose I'm going to replace all these batteries anyways, but I'll probably keep this one in a drawer somewhere because it may still be good to use in TV remote or something that's not requiring constant input. I'm going to measure my last battery in these series. And across my last battery, I'm still seeing that 1.4 volts. But let me also remove it from circuit, as I know my total battery voltage did not equate to 1.4, or the summation of both 1.4 voltage I was just now seeing. I can take an independent battery measurement, and I can see that this battery is also outside of the circuit, giving me about 1.44 volts DC. Maybe because there is corrosion around the terminal itself, that if I clean this up a bit, I could potentially just replace this one battery and use these last two. I could also say, because these batteries are different than this first battery here, this one could have been a lot older in age. I'm going to spin these batteries around a little bit, which will clean the terminals to an extent by breaking up that corrosion. And I'm going to remeasure between the first negative lead and the last positive. See if that produces any different results. As you can see now on my multimeter, I'm getting 1.32 volts DC. So it has made a bit of a difference. Now that I'm looking closer, I can see that I was a little bit mistaken between how they were wired up. You're actually going from negative lead here to positive lead here, positive to this negative lead, then positive out to the negative lead, negative side of this battery, and then positive out. Probably going to a wire or something feeding the electronic components inside. Now, as a way to also show you how you can use other things, the oscilloscope I have is a Signalant SD1052DL. It's a bottom of the range oscilloscope, but it still serves its purpose as a hobbyist. I like an oscilloscope, not just for taking measurements of a DC or AC value. I could also look at the RF spectrum through an oscilloscope. I don't have the equipment here to show you that, but I can do so because the inverse of frequency is time. And with an oscilloscope, your vertical measurements are a voltage, whereas your horizontal measurement is an adjustment over time. And the inverse of a specific frequency, if you take the inverse of a specific frequency, you would have a timed value of that frequency. I might not have said that correctly. Well, I want to show you this oscilloscope for a second. On this oscilloscope, I have a probe. Got it set to the 1 time scale. I'm not making a high voltage measurement, so I don't need to switch it over to 10 times by any means. If I press just probe 1, I have a menu here where I can change the coupling of this probe. You'll see right now it's set to DC, but I'm about to take a DC measurement, so the first thing I want to do is set it to ground. And by setting it to ground, then I'm able, oh nope, don't need to adjust intensity, but I guess I should, just in case if this is a little bit hard to read. You can see that I have a yellow line across my scope. And probably what you can't really make out, unless I get closer, is you have dotted lines. And basically, they fill up this entire section. It makes squares. One through your voltage range, up and down, vertical, and one through the horizontal time range. Now, I currently have my voltage set to 500 millivolts. And what that means, I'll explain here in a second. I can adjust the vertical, this vertical line here, excuse me, horizontal line, and I want to establish it somewhere at the bottom of one of these squares, and this I'll call my baseline reference. And what that means is, as soon as I touch the probe, you'll see that this right here increases, and the value is going to correspond to the value that I've set via my vertical scale knob here, increasing or decreasing the voltage range. If I had it set to 1 volt, then when I see a corresponding change up to this first square value, or let's say I'll set it up here. This is a little bit easier to view. If this increases by one value heading up this way, the next line, then that means that that value equates to about 1 volt DC. Now if it goes up to 2, then that would be 2 volts. Again, I want to set my measurement to 500 millivolts. As I know the multimeter was giving me about 1.5 volts, then I should see that this increases by not just 1, but 2. So 500 millivolts plus 500 millivolts will give me a volt, and almost up to this third line here for 1.5 or around 1.43, I think is what we were seeing. It shouldn't quite touch that line, but it's going to be a much more accurate measurement. Additionally, I can hit the measurement menu on my oscilloscope, and then somewhere on my measurement menu I can change the voltage to what I want to look at, whether it's VPP, Vmax, Vamp, Vtop, Vbase, whatever, or voltage average. I'm just going to set mine on Vmax because that's what I want to do. I can also have a function on the oscilloscope for an all measurement menu, which I could turn on. So instead of me doing the math myself, the oscilloscope will give me the math and display it down here. Let me see if I can somehow set this video to here. I'm going to keep this voltage on so you can see the corresponding changes down here. And then with my my probe, the pointed tip is going to go to the positive side of the 3 batteries, the last positive side, and my negative lead will go to the first negative side of a battery. And because I wasn't paying attention to how the batteries were wired up, I think we're going to see a better example of what our actual voltage is now. I have to go freehand for a minute. Oh, that's right. I forgot I'm still coupled to ground. So I do need to change that to DC to actually get a measurement. Alright, now we should be able to see something. Now if I wanted to take an AC measurement, I change my coupling to AC instead. Alright, my multimeter is giving me a voltage max of 500 millivolts, which is what we were seeing on that first battery. And a little bit of extra pressure I'm getting, 6.2 millivolts. As I go across my second battery, measure again just across the second battery. You see I went up almost 3 whole increments from our baseline, and we're getting that 1.8 volts that we saw earlier. Now I like taking a voltage measurement with my oscilloscope because, as you can see, I get an immediate corresponding reaction when I connect to my battery. The other thing that we're seeing on this oscilloscope is that yellow line. Now, why would it be important to actually have a yellow line to view, regardless of being able to see the voltage measured across on just a standard multimeter? Well, in a lot of circuitry, especially when you're converting, say, AC to a DC, it's done by developing a unregulated DC voltage. Before regulating those voltages, and power supplies, most traditional ones, you see them around positive 12 volts, negative 12 volts, 5.1, sometimes negative 5.1. Sometimes you'll see 3 volts. But the thing I'm looking for on that yellow line specifically, when I connect my leads to it, is I don't want to see a lot of spurious movement on that line itself. We call them peaks and jagged edges. Now, why is that important? Well, if I'm taking a voltage measurement, if that DC voltage is very dirty, is the term I'll use for it, or it starts to oscillate, meaning you start to see a change instead of it being constant, and it looks more like a traditional sine wave, then there's something wrong with the conversion from AC to DC. Maybe there's a filter, maybe the semiconductor devices, the diodes, the bridge rectifier, whatever it is bad itself, and that's one surefire way to check. But this is just a DC battery, and I'm checking it with my oscilloscope and talking through some things with you. I'll do the same with the last battery. And again, checking between the positive lead to the negative lead on that last battery, and forget the fact my hands aren't very steady. Getting a volt max 1.46, that's a little low for a 1.5 volt battery. Additionally, I'm not seeing any issues with the line from that battery, the actual yellow line. It tells me that there has been significant damage to this battery. It seems to be a pretty clean DC voltage. Comparatively, here's the bad battery. So we can see it's fully drained. So what I'm going to do next is I'm going to replace the bad battery, that one specifically, before I start swapping out all the batteries, with just one good one to see if it changes anything with the car itself before we start tearing it apart. All right. I've taken out the battery that's not giving us a good reading, and as you can tell, the terminals are fairly corroded. The bottom half is bulging out a little bit. This battery is definitely bad, and I'll be throwing it away. Now, even though I have corrosion on these terminals in here, as long as there is some type of continuity, physical metal to metal connection, I should be able to at least see, with this battery swapped in, if whether or not this equipment will work, or if I need to dig further into the repair. So I'm taking the 2 lower voltage batteries and this one new one and plugging it in, ensuring that the system, the switch is on the on position for sound. I'm going to check to see if anything happens. And still nothing is occurring. I'm also going to take the leads from my multimeter and recheck to see what voltage we're getting from battery to battery. And it's kind of interesting that when I go from the actual first negative rail to the last positive rail of this battery, I'm only getting half a volt. Even though now on this battery I've got 1.59 specifically here, .44 on this battery here. Oh, maybe it is a corrosion. And 144 here. Regardless, I am going to now dig into this a little bit deeper and start taking the entire thing apart to try to make this work again for my son. As this, even though it's pretty tore up, is one of his favorite toys. Alright, so there were 3 screws in the base, other than the battery cover screw, 2 in the back and 1 in the front right here. I've removed those, and now it should be simply disassembling and figuring out how to disassemble this. It appears most things are simply snapped in place. Alright, so that piece has a lip on it. It goes underneath here where that screw sits. That is now out. We've got lip here, back and lift. Now that piece is out. There is something sliding around here. Oh, that's pretty unique. And we'll try to figure out this back end piece as well. So the first thing I immediately found is this magnet is sliding around. Well, that's not good, because in order for a speaker to work, you need the magnet in it. I'll explain speakers in a minute. But we also weren't given given permanent lights either. So what we have here, albeit it's fairly damaged, a lot of damage. We've got a significant amount of corrosion on just the switch itself that turns on and off the sound, or on and off the system. Got a lot of dirt in the motor. Like I said, I have no expectations if there are any broken gears or anything to fully replace this. And it looks like the axle itself is dislodged from one of the gears as it's sliding around freely, which shouldn't be the case, as these gears should catch it in order to spin. I mean, I suppose I could tear that apart just so we could see it, but the places I'm going to currently focus on are the switch here because it's corroded. Alright, here's the back side of the battery case, or where the battery is being held. Looks like none of our wires have come loose from here. We have boards on the left side, these PCBs, and wires feeding to it. These PCBs hold the LEDs. That I think were red. You have resistors in here as well. Probably something to do with bringing the current down in order to make use of the LEDs. Typically, a D stands for diode. So these are LEDs, are light emitting diodes. So the polarity is important on it. What was presented on one side versus the other side, negative to positive. Because they're only turn on if the polarity is correct. Over on this circuit board, it looks like we have some more resistors, some more light emitting diodes. We have a nice diode here. It's pretty close to a positive and negative rail. I wonder if that's being used just in case of the batteries go in backwards, some kind of protection. Usually these same type of diodes could be used for something like that, or maybe some form of rectification. You see these J's right here? They're basically jumpers, but what these are zero resistant resistors, if I can put it that way. So instead of just jumpering a wire from pole to pole, what you have is a resistor. If I can get this to focus, not sure if it will. Are you going to focus? What you have is a basically a resistor with no resistive value. Things marked with Q probably have some type of transistor on the other side, similar to these devices here. Those are transistors. Transistors usually have 3 legs to them. Sometimes the base of a transistor will be a leg versus actually having a leg out itself. This U right here typically stands for a comparator, but there's probably, without having a diagram, there's probably it's probably some form of gate, which is basically, you know, multiple inputs and what has to happen at those inputs in order to produce an output. But I'm willing to believe that this is probably the brain box of the entire thing. I don't see any wires that have broken off, which is a good sign. But the main thing we have is the fact that one, there is a lot of cleaning that needs to occur. There is corrosion that needs to go away, and we do have the magnet that's fallen out of this speaker. Now I want to show you something. You have a negative and a positive lead on the magnet. You have a diaphragm in here on one side of the speaker, as well as a coil. And then the magnet sits on top of the coil. Let me grab a piece of paper and I'll explain some of these things.